Good afternoon, everyone. Today is my pleasure to introduce my colleague and friend, Sasa Cigoja. And Sasha started here as an intern in his undergraduate, where he came from University of Applied Sciences, Technicum Vienna, and he worked on the biomechanical effects of wearing a sacroiliac belt. And at the end of Sasha's internship, that's when I started here in the HPL about 3.5 years ago. And at that point, Sasha was going back home, where he started to work with Adidas. And now here we are about 3.5 years later, and Sasha's in the 3rd year of his PhD. So I want to know, Sasha, what went wrong? You started a job and now you came back to the university. But so in 2016, Sasha started his master's, where he focused on the relationship, or where he's currently focusing on the relationship between subject-specific characteristics and optimal bending stiffness of footwear as it pertains to running or track and field athletes. That might have inspired him to fast track into his PhD. Sorry, I had to do it. And where he's now continuing to do that with Dr. Ben O'Nig. And mostly what I do in the BioSketch is have the people fill out a number of different parts of the BioSketch, including their education. And for Sasha, when talking about his PhD, it says graduate starting year would be 2018, where he did the fast track. Kinesiology is the program, University of Calgary, Canada is where it is, and it's specialization of biomechanics. Expected graduation year, 2,999. So I don't know if that was a typo or maybe some foreshadowing for Sasha. And one interesting fact from Sasha is that he was recently winner of the 2018 International Sports Engineering Association Student Project Competition, which was a competitive competition where you created an innovative project idea, gave the proposal, and people were rated, which Sasha was first place. And when asked Sasha about some interesting facts about him, in a typical Austrian fashion, he gave this very plain fact. I shipped about 12 pairs of Adidas shoes from Austria to Canada when I moved to Calgary. I got these shoes while working as an intern in the company. So I was hoping Sasha would have some more interesting facts. But here's some that I thought of. So he worked in the Red Cross, where he learned invaluable lifelong skills. The second one is that he wants to work in the footwear industry and does research on footwear, but he hates looking and even touching even looking at sweaty feet. And when Sasha started his master's, we were out having a drink, and I ordered a sour beer, and Sasha said, what is this? And so he took a sip and he said something like, "That's not beer." But sure enough, if you ask Sasha now, 2 years into his PhD, what his favorite beer style might be, you'd probably say it is a sour beer. So without further ado, Sasha today will be talking about subject-specific characteristics and midsole bending stiffness of soccer cleats. Floor is yours, Sasha.
Thanks, Mike. I guess.
That was very genuine.
With significant advancements in automated manufacturing techniques such as 3D printing, individualized footwear solutions can be created. However, in order to be able to offer these individualized footwear solutions, athletic footwear companies are trying to match the product to their consumers' characteristics. Previous studies have tried to match footwear solutions to subjective preference of perceived comfort. However, the footwear industry is also interested in offering footwear solutions that allow to increase athletic performance. A shoe has many different features, and each one of these features could potentially affect performance. One of the footwear characteristics that has been shown in previous literature to have a great effect on performance is the midsole bending stiffness. The research on midsole bending stiffness of sports shoes started initially with these two publications by Stiffness and Nig in 97 and 98. The purpose was to investigate the energetic contribution of the metatarsophalangeal joint during athletic activities such as sprinting and jumping. So here we have in both cases the metatarsal power as a function of normalized time from heel strike to toe off. And on the left-hand side, for the sprinting task and on the right-hand side for the jumping task. The main findings of both studies were similar in the sense that the MTP joint is mainly absorbing energy during athletic activities. This is indicated by the area between the negative portion of the power curve and the horizontal axis. However, the amount of generated energy in the joint is minimal. That would be the positive area, or the area between the positive part of the curve and the horizontal axis. Also, the amount of energy absorbed for the sprinting task was about twice as high than for jumping. Now, the MTP joint absorbed lots of energy due to the fact that it's mainly dorsiflex during stance phase. Therefore, if one would want to increase athletic performance, the amount of dorsiflexion and therefore the amount of energy absorbed in the joint should be decreased. And one way to decrease the amount of dorsiflexion of the MTP joint is to increase the stiffness of a shoe. Therefore, the hypothesis was that increased stiffness will also increase performance. The first study to test this hypothesis was performed by Stefanishin and Nig in 2000. The authors investigated vertical jump height when performing the task in a control and a stiff shoe. And indeed, their findings show that when participants were performing the task in the stiff shoe condition, they were jumping significantly higher compared to the control shoe. The interpretation was that increased bending stiffness reduced the MTP joint dorsiflexion and therefore also reduced the amount of energy absorbed in the joint. And that led to increased jumping performance. Based on the studies from 97 and 98, where it was found that the amount of energy absorbed is about twice as high in sprinting than in jumping, it was hypothesized that a similar performance benefit will be observed when have individuals perform sprinting tasks in a stiff shoe. So this study investigated sprinting performance in national and varsity athletes and investigated the sprinting performance in 4 shoe conditions. The own condition is each individual's own sprinting spike, and the other 3 stiffness conditions were achieved by inserting different levels of, different carbon fiber plates into the shoe. The study showed that about 85% of the participants performed best in one of the stiffness conditions, whereas about 5 participants performed best in their own sprinting spike. Also, you can see that some individuals perform best in the stiffness condition 42, some of them perform best in stiffness condition 90, and some of them perform best in stiffness condition 120. So it appeared that the bending stiffness that results in best performance is also subject specific. On the bottom part, you can see the relative improvement with a stiffness condition compared to the subject's own sprinting spike. And there are a few individuals that, for example, subject 13 and subject 28, that showed no improvements when sprinting in a stiff shoe condition compared to their own sprinting spike. However, there were also a few individuals who performed better in their own condition compared to their best stiffness condition. But the majority, however, improved performance when they were executing the task in a stiff shoe condition. Here we have some exemplary subjects, subject A on the left and subject B on the right. We have the 20-meter sprint time for all 4 shoe conditions, standard being each subject's individual shoe condition. What we can see is that subject A has lowest sprint time and therefore highest sprinting performance in shoe condition 90, whereas subject B has lowest sprint time in shoe condition 42. It means that the level of midsole bending stiffness that leads to best performance can be different between individuals. A study performed by Viano and others investigated the effects of bending stiffness on physiological and performance variables during a soccer-specific in-game scenario. The authors found significant improvements in physiological measures, but no differences in performance. Even though, on average, the stiff shoe condition resulted in best physiological outcome, there were still some individuals who who showed lowest or best physiological measures in the low stiffness condition, some in the medium stiffness condition, and some in the higher stiffness condition. This further supported the notion that there is an optimal stiffness, and a stiffness that is either too low or too high is not beneficial. Also, the existence of an individual optimal bending stiffness was supported. Now we know that soccer cleats have specific characteristics that can influence performance. We also know that athletes have specific characteristics such as anthropometrics or body strength that can also affect performance. But what we don't know yet is how these soccer cleat specific characteristics are connected to subject specific characteristics. Therefore, the goal of this study was to investigate whether or not soccer cleat specific characteristics such as the bending stiffness are related to subject specific characteristics, and if there is a relationship, to determine how they are related. For this reason, we performed a total of 6 what we call functional assessments. We use those assessments to describe our participants in as much detail as possible. These assessments included anthropometric measures, balance scores, variables describing foot posture, sensitivity scores of the feet, an estimate of whole body strength using the grip strength, and an extensive biomechanical dataset. Ultimately, the goal was to provide a list of variables that are simple to assess in a realistic in-store scenario that footwear companies could use and implement in their stores to make recommendations on which bending stiffness someone should perform in based on their characteristics. The anthropometric variables included 24 measures. The variables were, among others, body mass, foot length, shank circumference. All of these variables were either measured by hand or using a 3D foot scanner. During the balance assessment, we determined subjects' balance and flexibility using the Y-excursion balance test. For this, individuals were standing on a platform in the middle and were trying to push the other platforms as far away as possible. After a given familiarization period, they performed one trial where we measure each reach or the reach in all 3 directions. The test was then performed with both legs. The next assessment focuses on determining variables assessing or describing foot posture. On the left-hand side, we have the arch index, as described by the methods by Kavanagh and Rogers, which basically looks at the area of the midfoot relative to the overall area of the whole pressure pattern during overground walking. On the right-hand side, we have a variable that we call Varus score, which is used to describe how much the center of pressure trajectory, which is illustrated here by the green line, deviates from the angle bisector line, illustrated here by the black line. Both these measures were assessed using a pressure plate. The next assessment is used to determine the sensitivity of the participant's feet. For that, we used monofilaments that are basically fishing wires of different stiffnesses that we then use to apply pressure at different locations of the foot, the great toe, the first and fifth metatarsals, medial and lateral arch, and the heel. We then obtain sensitivity scores based on the lowest pressure threshold participants are able to perceive. And this was done for the kicking foot only. In order to obtain an estimate of whole body strength, we measured the grip strength using a hand grip dynamometer. Subjects were performing 3 maximum voluntary contractions using their dominant hand. Grip strength has been shown to be significantly related with knee extension force. Therefore, we thought that this measure would be a good indicator for the strength of a soccer player, because knee extension is the major motion for soccer-specific tasks, such as kicking. Lastly, we also collected an extensive biomechanical data set consisting of a bilateral marker set that allowed us to determine metatarsophalangeal, ankle, and knee joint kinematics, as well as ground reaction forces during the soccer-specific tasks. However, for today's presentation, please note that the biomechanical data was not included in the analysis. For the performance protocol, we had 55 male recreational soccer players participate in this study. They all performed 3 soccer-specific tasks, 6 maximum effort soccer kicks, 6 5-meter sprints, and 7 counter movement jumps. The tasks were performed in 5 stiffness conditions, or in 5 shoe conditions. The soccer cleats were the exact same cleat model. The only difference between the shoe conditions was the stiffness, the midsole bending stiffness. And for that was altered by inject molding different amounts of plastic material in the midsole during the creation process of the cleats. The stiffnesses ranged from 100 to 447% of the most compliant stiffness condition. We then grouped our individuals based on the performance, or based on the stiffness condition they have performed best in. And for that, we used the maximum ball speed, the lowest sprint time, and the maximum jump height. And how this grouping looked like is presented here. We have representative performance data for 2 subjects, subject 20 in green and subject 16 in orange. Ball speed, or kicking performance in form of ball speed in kilometers per hour, what is represented by squares and linked to the left vertical axis. Jumping performance in form of jump height is represented by circles and linked to the right vertical axis. Performance measures were plotted as a function of stiffness from C1, most compliant on the left, to C5, stiffest on the right. What we could see is that the bending stiffness that led to best performance for one individual can differ between tasks. So here we have subject 20 performed the jumping task best in cleat 3, but performed the kicking task best in cleat 5. What we were also able to observe was that different individuals were performing the same task, or showed best performance for the same task in different stiffness conditions. So we have here subject 20 performed the kicking task best in cleat number 5, and subject 16 performed the kicking task best in cleat number 1. This suggests that the best performing midsole bending stiffness is not only subject specific, but also task dependent. And for that reason, we grouped our participants for each task respectively. Here we have the frequency distribution for all soccer-specific tasks across the 5 stiffness conditions. On the vertical axis, you can see the number of times a given stiffness condition resulted in best performance. And on the horizontal axis, again, the 5 stiffness conditions from most compliant C1 on the left to stiffest C5 on the right. The pattern bars represent how many times a given stiffness condition resulted in best kicking performance. The white bars represent how many times a given stiffness condition resulted in best sprinting performance. And the empty bars represent how many times a stiffness condition resulted in best jumping performance. The numbers on the top are basically the sum of these bars and should illustrate how many times a specific stiffness condition, in this example, cleat number 1, resulted in best performance across the 3 tasks. And what we can see is that all stiffness conditions are fairly equally represented across the 3 tasks that individuals have performed. That means that all 5 stiffness conditions were used in our study, and there was a need for this range of stiffnesses. There were 4 major steps that were included in the data analysis. We had an initial data set of 64 functional variables, and some of these variables were related to each other. In order to decrease the collinearity in our data set, we performed feature selection by correlating every single variable with each other. That gave us a correlation matrix that looked like this, with variable 1 to variable 64 in the rows, and also variable 1 to variable 64 in the columns. On the diagonal, we'll have the correlation coefficient of 1, because this is where one variable was correlated to itself. We then determine an arbitrary threshold of 0.8 for the correlation coefficient. This means that if 2 variables are correlated and they present a correlation coefficient of 0.8 or higher, one of these 2 variables is eliminated from the data set. Typically, the variable that was simpler to assess in a realistic in-store scenario was chosen to remain in the data set, whereas the variable that was more difficult to assess was eliminated. This reduced the data set from 64 variables to 43. So that means we eliminated around a third of the initial input variables, which means that they were measuring different characteristics of our individuals. We then performed mean normalization of the reduced data set and also performed feature scaling using the standard deviation. This reduced and transformed data set was fed into different machine learning approaches, the linear discriminant analysis, the support vector machine, and the multinomial logistic regression. Lastly, to validate the performance of our machine learning tools, we used the leave one out method. The outcome measure of our machine learning tools was the classification rate of how likely the tool is able to predict the best performing midsole bending stiffness for a given individual. Imagine we have a subject who performs a soccer specific task, and he performs best in stiffness condition number 2. For us, in order to count the prediction of the machine learning tool as a correct prediction, the predicted best cleat had to be exactly the same stiffness condition as the one that the person performed best in. This is what we call the absolute classification. However, for footwear industry, it is sometimes sufficient or satisfying enough to be able to give a rough recommendation towards a more compliant cleat or a stiffer cleat. And therefore, we determined also the one-off classification rate. In this scenario, imagine again, the same person performs best in cleat number 2. But now for us to accept the predicted best cleat or the prediction to be correct, we allow the machine learning tool to be at most one stiffness category off from the actual best cleat. Now, if a subject performs best in conditions 2, 3, or 4, the machine learning tool has 3 out of 5 options to give us a correct prediction. However, if we have someone who performs best in either the most compliant condition or the stiffest condition, the machine learning tool has now only 2 out of 5 options to give us a correct prediction. And this is important to consider when trying to make a statement whether the classification rates that were obtained are better than obtaining these classification rates simply due to chance. In order to determine what the level of chance was, we performed a Monte Carlo simulation. In brief, the Monte Carlo simulation uses random numbers to simulate what the probability is of obtaining a classification rate simply due to chance. So if we perform a simulation using 55 subjects and we want to predict the best performing stiffness conditions out of 5 conditions, and we allow the machine learning tool to be at most 1 condition off, and we repeat this simulation 100,000 times, we will observe a distribution that looks like this. We then take the classification rate that occurred most often and determine this as the one-off chance. And then for the one-off scenario, that was 53%. Here we have the absolute classification rates of successfully predicting the best performing level of midsole bending stiffness for 3 soccer-specific tasks using subject-specific characteristics. On the vertical axis, we have the classification rate in %, and on the horizontal axis, we have the 3 tasks, the kicking, the sprinting, and the jumping task. The green broken line represents the level of absolute chance, which was 20%. The absolute classification rates were about 32, 27, and 35% for the kicking, sprinting, and jumping task, respectively. The type of machine learning approach that was used to obtain these classification rates only affected the results minimally. The absolute classification rate was only minimally above the level of chance, which is obviously not very satisfying. However, when we look at the one-off classification rates, we have 76%, 67%, and 77% for the kicking, sprinting, and jumping task, respectively. And similarly to the absolute classifications, the type of machine learning approaches affected the classification rates only minimally. Although the one-off classification rates were much higher than chance, we are still only successfully classifying at most 3 out of 4 participants. Here we have the type of assessments that were used to measure the input variables to the machine learning tools that resulted in highest classification rates. And predominantly throughout the 3 tasks, variables that were assessed using the anthropometric or the foot posture assessment resulted in the highest classification rates. However, variables that were targeting the foot sensitivity and grip strength were not used as, or were not chosen as predictors for the best performing midsole bending stiffness. When we go back to the list of assessments that we had in the very beginning, the assessments that measured the variables that were used to determine highest classification rates were mainly anthropometric and foot posture variables. And this is what we expected, or at least hope to see, that variables that are associated with the foot and describe anthropometrics of the foot will also be in some way related to the level of midsole bending stiffness someone performs best in. However, when we look at the one-off classification rates, the machine learning tools also use some balance scores to increase the classifications. And for that scenario, we don't really have a good explanation why specific balance measures are being used to increase classification rates. Variables targeting the sensitivity of the feet were not identified as very good predictors by the machine learning tools. And this may not be as surprising because the sensitivity of feet may be more important when it comes to questions about perception, such as comfort, and not necessarily performance. Although the grip strength as an estimate of whole body strength may have been a bit of a far-fetched, we were still surprised to see that it has not been used as a predictor, or has not been identified as a strong predictor of best performing midsole bending stiffness. Because it has been shown that grip strength is associated with knee extension force, we were hypothesizing that it could be used as a replacement measure for actual knee extension force as an estimate of whole body strength, but this was not the case. Probably one of the main limitations of this study is that no information was obtained about the muscle. The muscle is where force is generated and which causes motion, and it has also been showed in previous literature that the bending stiffness of a shoe is able to affect the gear ratio, for example, of the musculoskeletal system, and helping to optimize for muscle function. Therefore, information on the muscle's ability to generate force, its force-length relationship, its force-velocity relationship, or best case scenario, its in vivo behavior while performing athletic tasks in different levels of midsole bending stiffness could help to explain the mechanisms behind why different individuals need different levels of bending stiffness to increase the performance. Another limitation of the study was that we did not control for the fit of the cleats. We had soccer cleats in sizes 9 and 11, and individuals were able to try them on before testing. And if they said that this is the size they would typically play soccer in, then they were able to participate in the study. However, it's possible that some cleats were fitting some individuals better than others, and therefore there may have been some movement of the foot within the cleat that could have affected performance. There is still an extensive biomechanical data set associated with this study, containing 19 maximum effort trials per condition, times 5 conditions, times 55 individuals, which equals to more than 5,000 trials of kinematic and kinetic data that could potentially be used to relate subject-specific characteristics to midsole bending stiffness that results in best performance. However, the biomechanical data is more interesting from an academic point of view and is most likely not very feasible to implement in a regular footwear store. The purpose of the study was to investigate whether subject-specific characteristics are related to the level of midsole bending stiffness someone performs best in, and if so, to determine how they are related to each other. In order to answer this question,